A lump of material might have roughly 10 to the power 23 or so atoms or electrons in it. How can we begin to think about the quantum mechanics of something as complicated as that? Any given electron will experience attraction from the nuclei. The electron is negatively charged, and all of those nuclei from the atoms are positively charged. And it will also experience repulsion from all the other electrons. So there is some possibly very complicated interaction going on here between these approximately 10 to the power 23 charged particles. The key first approximation we make is to presume that any given electron sees a periodic potential. That is, some potential that is periodic with the same periodicity as the crystal lattice. This supposed approximate periodic potential arises both from the charged nuclei, which are presumed to be fixed in space in this approximation, and from all the other electrons, whose charge distribution is also presumed to be effectively fixed. Note this is only an approximation. Any given electron state will tend to distort the crystal lattice by pulling on the nuclei. Any given electron state will also, in reality, interact with other electrons. Our hope, however, is that we can handle such other interactions as perturbations. Hopefully, the results we'll get from this so-called one-electron model can then be used as the unperturbed solutions. So let's see how we set this up. So, in our one-electron approximation, we presume that we can write an effective periodic potential. So some potential Vp here that is the same at a point r plus any lattice vector as it was at the point r. So these are any of the possible crystal lattice vectors that take us from a given point in one unit cell to the same point in some other unit cell. So this is a way of writing down our presumption that this potential is periodic with the crystal lattice periodicity. And therefore, we have an effective approximate Schrödinger equation, which is for the one electron in which we are interested. So that's this equation here, a Schrödinger equation with this presumed periodic potential in it. And this is our one electron approximation. So to summarize, we have presumed, at least as a simplification, that for any one electron we can pretend that it sees a completely periodic potential. And that's what we put in our Schrödinger equation. And this periodic potential is the sum of the effects of all of the other electrons and all of the other nuclei. That's our presumption in the one electron approximation. Now, in one dimension, of course, our crystal should be periodic with this repeat length, whatever that is. This is the length of our unit cells, and for the moment we're talking about one dimension. And so we should have the same potential at some point x plus s times a as we have at the point x. And of course here s has to be an integer. So we're merely moving over by some integer number of unit cells in this one direction. So any observable quantity must also have the same periodicity, because the crystal has to look the same in every unit cell. Now, this gives us some consequences for the periodicity of psi squared, the probability density of finding an electron. So for this probability density then, for example, explicitly, we expect the charge density to be proportional to that. So it has to be periodic in the same way here. Hence, we want to say that the charge density or the probability density at some point x plus a has to be the same as it was at the point x. Now, that doesn't mean that the wave function has to be the same, because the wave function is not really necessarily an observable quantity. But something like charge density should be the same as we move over into the next unit cell as it was in the previous unit cell.
because charge density presumably is a measurable property. And so that means that the wave function at point x plus a has to be the same as the wave function at point x within some unit complex number, a unit amplitude complex number. That's something like exp I theta, or e to the I theta. There is no requirement, just to repeat, that the wave function itself is periodic with the crystal periodicity, but something measurable like charge density must be. And this is because the wave function is not apparently an observable or measurable quantity. We can say that this must be true, that the wave function at point x plus a has to be some unit complex number times the wave function at point x, because we expect that the charge densities or the probability densities have to be the same at the same points in different unit cells.
As is often the case, the boundary conditions lead to the quantization of the problem. Remember the hard wall boundary conditions for the particle in a box. We had infinitely high walls there, for example. These led to the standing sine wave solutions that fit between the walls. But what kind of boundary conditions represent a crystal? The catch is that our idea of a crystal is, by mathematical definition, something that goes on forever. How can we introduce some set of boundary conditions, ones that give us the quantization, but that also allow us to count the available states correctly? This ability to count the states is quite important in understanding crystals. Without it, for example, we can't figure out how the finite number of electrons in some finite piece of crystalline material will distribute themselves among the various possible states. If we can't figure that out, we can't calculate all sorts of important properties, such as electrical conduction or optical absorption. How can we introduce the concept of the finiteness of the crystal while still exploiting the beautiful properties of a perfectly and infinitely periodic system? The trick here is to introduce what are called periodic boundary conditions. These actually can make perfectly good sense in a one-dimensional system, and we can get away with using them in other cases also. So let's see how we set these up, starting with the one-dimensional case.
So, in one dimension, we could argue as follows. We could suppose that we have a very long chain of n equally spaced atoms, and that we join the two ends of this chain together. So here's our chain, going all the way around in a circle here, and we've joined the two ends of the chain together to make this circle. And here we're taking the case where n, the number of atoms in the chain, is 12. And here's our repeat distance along this chain, A. So, with x as the distance along this loop here, then, on this loop, the potential can be written in the following way. If we move some number m times a, and we'll make m an integer, of course, along the chain, we will get the same potential at that point as we had at our original point. So some point on the chain here, and we move along by some integer number of these repeat lengths, and we should have the same potential. That's what we're saying here. And note that this will work even if m is an integer that is much larger than n. We could just keep going around a circle many times. It would still be true that as long as little m here was an integer, then this kind of relation would still hold. Now, this expression that we're looking at here is just like the one that we had for the periodic potential in an infinite crystal. And we can make the following argument, at least for a one-dimensional system. We can say, well, if this chain is very long, its internal properties will not really be substantially different from an infinitely long chain. The fact that it's bent a little bit, we presume, won't really matter if the chain is very, very big. So we presume then that this kind of approach is actually a good enough model that gives us a finite system, so this chain only has a finite length, while still keeping these periodic boundary conditions. And this is the trick of periodic boundary conditions. We can work with a finite system that nonetheless behaves more or less the same as an infinite crystal would behave, at least for this kind of periodic potential. Now, this loop gives us a boundary condition. We do want our wave function to be single-valued. Otherwise, how could we differentiate it or evaluate its squared modulus and so on? So we presume that going round the loop, the wave function must come back to where it started. It must be the same value when we went all the way around the loop as it was when we started at a given point on the loop. So that means that psi of x, the wave function at point x, should be equal to psi of x plus capital N times our repeat length. That is, if we go all the way around the chain, which is what we're doing here, adding on a distance capital N times a here, we're getting the wave function back to where it started. So this wave function should equal that one. And this is called a periodic boundary condition. It's periodic here because we go round a number of periods and we get back to where we started. And we could keep on going with x, of course, and this would still be true. X can be as large as we want, and this condition still applies. We could imagine we keep winding round this loop if we want to. So we would always get this periodic behavior in x if we just kept on going with x, for example.